All right, well, we're going to begin with a review exercise today. So if you have your calculator, go ahead and get that out and ready to go. Exercise 30, there on page 26. So page 26 in your review exercise and speed drill booklet. And something you talked about in 7th grade is this idea of compounded interest. Do you remember learning about compounded interest, where you pay interest, but every month more interest just keeps getting added on? This is used anytime that a loan is financed or items are financed. So simple interest is called simple because it's just I equals PRT. But in reality, interest is compounded a little bit. So let's take a look at this purchase here. We'll read the directions first. Well, it says on many loans, interest is calculated each month based on the remaining balance to be paid back. Using a calculator, fill in the chart. You'll do the first few rows with your teacher. This chart is based on the following scenario. Matt Presley purchased a piano from a music store in July. No payments for a month. And will make monthly payments for 1 year. He bought the piano for $2,000, which isn't that much actually, and will pay 24% interest. Now, 24% means monthly is 2%. Does that make sense? Everyone understand how we got 2% from 24? Divide by 12. All right? He'll pay $200 a month until the last month in which he will pay off the balance. So you'll notice August is already done for us. As of August, because he didn't make any payments in July, his August balance was $2,000. Well, again, interest is calculated 2% of that. So how would you do that on your calculator? Go ahead and do it on your calculator now. Take the 2,000 times 0.02. And you should get $40. Is that correct? And you see that filled in there. Right? Making sure Lana's good to go. Which means his balance now is $2,040. $2,000 he did owe, plus the $40 worth of interest. So really he owes $2,040. Do you see how that next column is figured? He's going to make monthly payments of just $200. So he pays $200 off, which means he now only owes $1,840. Do you see that? We subtract the $200 payment from his balance and interest that he owed before. Now notice how the new balance carries down to the September line. That's what he owes when the month of September starts. So let's figure what his interest is going to be now.
Does it have a clearing button?
I think if you just hit on, it clears it. So
yeah, it does.
All right.
Okay.
So again, we're going to take the 1,840, multiply that times 0.02. And what's his interest, Joshua?
$36.80.
Good, go ahead and write that in. $36.80 in interest. Now, that means, Lana, that he really owes how much money? Take what's on the calculator already and add the 1,840 to it, 1,840.
$1,876.80.
I think you mean 1,876?
Yeah.
Yeah, $1,876.80 is correct. You threw Josh off when you said 10,000. He's like, what?
I read it wrong.
It's okay, $1,876.80. Now he's going to make a $200 payment. I think you can do this in your head. If he makes a $200 payment, what's the new balance now, Lana? So you're going to write in the $200 for his payment, because that's just his payment every month. And what is his new balance?
I keep writing the numbers wrong.
You should have already had the first number on your calculator. So you don't have to retype it if it's already on the screen. You just do minus 200 and go from there.
$1,676.80.
Good, $1,676.80. Joshua, did you have that also? All right, now that becomes his balance for October. So now just rewrite the number another time for the October balance. So this is how much he owes now. We're going to rewrite that for October. because it's the same number. It just carries down to the next month. Now figure his interest and call it when you've got it.
$33.54.
Good, $33.54.
Yeah. What?
And obviously it doesn't come out evenly, it's 33.536, but you're going to round, 33.54. All right, now we're going to add the 33.54 to the 1,676.80 to get what? Updated balance plus interest. Okay, and again, Lana, all you do is hit plus 1676.8. You don't have to retype the number that's already on the screen. That wastes time. We're lazy.
Well, I typed the number wrong.
Oh. All right, so what's the balance plus interest now?
Do you want to say
Sure.
$1,710.34.
Good, $1,710.34. All right, how much is he going to make in his payment?
well, $200?
$200, because
Oh.
it's just figured you make the same payment every month until the final last month, which will usually be a little less than $200. Then once you get to that, or if the last month, like you get down, it's like, oh, it's $203. Instead of making $200 this month and then $3 the next month, well, you might pay it off extra, but usually pay it off until that last month is less than $200 because you won't owe that much. All right, and so what's his new balance now? Now that he paid off the $200.
$1,510.34.
Right, you see, all you have to do is subtract a 2 from the hundreds digit, because you're subtracting 200. So literally you can do that in your head. You don't need to enter that on the calculator. Go from 1710.34 to 1510.34.
Oh.
Okay, do that step in your head most of the time. It's really easy to do. All right. All right. Go ahead and fill in the November row. Go ahead and fill in the November row. Just the November row.
I think I remember doing this now.
And of course, companies now have spreadsheets. You've had computer applications where they would program it to do all these numbers for them. They just type in a number, let all the formulas do their magic, and that's how they're able to come up with this. We, of course, are working it out with a calculator and a table, but hopefully, just from computer apps, you're like, okay, yeah, I see how a spreadsheet could do this.
Oh.
Yes, you're filling in the November row. You should notice that the interest amount gets less and less every month because the balance gets less and less every month. All right, check your row. Should have started with $1,510.34. Then should have had $30.21 for the interest, giving them a balance plus interest of $1,540.55. Makes a $200 payment. Ending balance should be $1,340.55. Good to go? All right, do the December row. And I'm just going to give you the number at the end of the row once you're done to make sure we're good to go. And then I'll let you kind of finish the table out on your own.
they saying 10,000?
So what did you type? Okay, you should have started with the 1340.55, right?
Mm-hmm.
And you multiplied that times 0.02, right?
Mm-hmm.
And you hit that plus the 1340.55.
It kept adding a zero. I did it like 4 times.
I don't know if you accidentally hit 2 zeros. Maybe instead of maybe you hit the point late. I don't know. All right, Joshua, let's see what we've got there at the end of that row. Yes, go ahead and finish out the chart. Good. All right, go ahead and finish out the chart. That number at the end of December, Scott, should be $1,167.36. All right, that got you through Christmas, through the new year. All right, he's got 7 more payments, 7 more months to go. Go ahead and calculate this out. That's why we have a calculator for this one. This without a calculator would be pretty much impossible. Well, it'd take forever anyway. It wouldn't be
take us
impossible.
like half an hour.
Which is why I made the exception. Make sure that our numbers are still looking good.
Are they good still?
Yours are, mine aren't. Ours disagreed and I checked and I was like, no, he's right and I'm wrong. I guess I might have been trying to do this in my head or something, and that probably wasn't a good idea. I'm gonna have to refigure my numbers here. What good is an answer key when it's wrong, right? done, but I've got through April, so let me see where you're at. Yeah, you're still good.
Wait, so the last one in the payment should be 0 because it says he paid it off?
Well, because his last payment isn't going to be 200. It's going to be something different that allows him to pay it off. So, for instance, if he gets to the end and he only owes $87, then his last payment will be 87 to finish paying it off. So if you keep working it out, it'll get down to the end. So his last payment's not going to be a $200 payment. It's going to be something else. Good. You're good through April. So Josh at the end of March has 626.73, which is good, and you're a little bit ahead of that, Lana. Still good to go. And the 439.26 at the end of April, leading into May. Yeah, slightly rounded, differently rounded number. I got 05 here at the end. 448, $248.05. That's what round up to 0.0.
Oh.
Yeah. So $248.05 at the end of May. 2 months to make payments. Yep, and Lana's going to finish it out. So what's his last payment going to be? If he pays 200, he's paying too much, right? Because all he owes now is this. So guess how much he's going to pay? That.
Oh.
Yep. Because that's all he owes. That's all he's got left on his bill.
That's true.
Everything else is paid off.
That's not very much.
So Lana, since you're done first, if you'll do this for me, and there's a quick way to do it, would you add up all his payments for me? Would you add up all his payments?
Are we gonna have to add all these things?
No, just the payments. That's all I want to know is how much was his total payment? And Scott, if you are finished, you can add up total payments as well. I got a little bit different than you here. I did not get 896 right here. I had 496. Yeah, possibly. So I may have just misread it, which means this would be 253.01. Which means after he pays off his $200 at the end of June would be 53.01. You somehow got an extra $4 in there. I'm not quite sure how. So end of June, 53.01 was his total, which means as he heads into his last month, he owes 53.01. He's going to get stuck with just a tiny bit of interest on that. What was his interest that last month, Josh?
53.
And that's how much he owes. How much was his interest? It looks like you just punched it into the calculator.
I did, but for some reason I got off the same track.
Okay. All right. What was his interest that month?
$1.06.
Just $1.06 that month because he didn't owe much anymore. So his balance plus interest comes to
$54.76.
So how much will he make in his last payment? Yeah, $54.07. That's all he owes now. So that's all he'll pay. And of course that means his balance will be zero, meaning he's finally paid off the piano. Now, Lana, I asked you to add up all his payments together. Did you get that number? What would be a quick way to do it? Josh, while she's figuring the number.
I got 2,254.37.
Yeah, $2,254.07. Think about it. If you count it up, he did 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 months of $200 each, which is $2,200. Plus, he had a month that was $54.07, right? His final month of payments was very small. So that's the quick, easy way to get this for his total payment. Now, question: how much was the piano supposed to cost him? $2,000. So if he paid $2,254.07, how much interest did he pay? Don't overthink this.
$254.07.
$254.07 because he was only supposed to pay $2,000. He paid $254.07 more than that, which means the piano store, the music store, made $254.07 doing absolutely nothing but waiting on the payments that he was making. All right, questions on compounded interest. And again, do you see why they invented spreadsheets? Because people don't want it. Even with a calculator, it took us 25 minutes.
20?
We spent 25 minutes working on that. I knew it would take half the hour. We have a short lesson today, but can you imagine doing that calculator all the time? No. Spreadsheet, you type in the formula, let it do the work. Love spreadsheets.
I literally typed out page 200. That was stupid.
Well, but you learned a lesson from it, right? You learned, oh, note to self, do it the quick way. Right? All right, let me go and collect those from you. And take out your homework, if you would, please. Turn your books to page 507. Page 507.
I mean, it wasn't as much as writing it all out.
That's true. It still wasn't as bad as working it by hand. That would have been pretty awful. Page 507, and we began talking yesterday about roots, and basically said the root is the opposite or the inverse class of a...
No, wait, what?
What is the root? A root, the opposite of? An exponent. Good. An exponent tells you use this number as a factor this many times, you get a really big number. A root says I've got a really big number. What number was used a whole bunch of times? For instance, if I said, what is the fifth root of 32? It's asking what number times itself, times itself, times itself, times itself could have given us a 32. Just for the sake of fun of it, hazard a guess. Anyone want to make a guess? He guesses 4. All right, let's try it. 4 times 4 times 4 times 4 times 4. All right, what's 4 times 4?
60.
Times 4.
64.
64. That's already too big, so it can't be 4. Let's try a smaller number.
Is it 2?
All right, let's try 2. All right, 2 times 2 times 2 times 2 times 3. All right, 2 times 2.
4
times 2.
8
Times 2.
16
Times 2.
32.
Bingo, there it is. Apparently 2 is the fifth root. And again, the root just says what was used as a factor a whole bunch of times. So a root is simply the inverse or the opposite of an exponent. We said that in an expression like this, this goofy looking root symbol has a name. Alana, do you remember what we call that thing?
Radical sign.
The radical sign. This little number that tells me which specific root, because there's all kinds of roots, right? Just like there's squares, cubes, fourth powers, fifth powers, sixth powers, seventh powers, eighth powers. Well, there's square roots, cube roots, fourth roots, fifth roots, sixth roots, seventh roots, eighth roots. There's all kinds of roots. The little number right here, raised like an exponent, but it's not called an exponent, that tells me which root we're taking, Josh, is called the index. Good. So we have our index. We have the radical sign, or the book calls it the radical symbol, but radical sign is fewer syllables. And then we have this number in here that tells me what number we're taking the fifth root of. And that line, in this case, this number is called the
Radicand.
radicand. Very good. So we have the index, the radical sign, and the radicand. And you were identifying some of these things in the homework last night. Page 507, number 1, it says, identify the radicand and the index. Well, what's the radicand there, Josh?
8.
And the index is?
7.
And how would we read that radical?
The 7. Yeah,
What's that symbol mean?
The root.
Root, seventh root.
Of 8.
Good, the seventh root of 8. Let's see, number 2, Lana, that's a doozy. How would we read that, Lana?
Fourth root of 16,486.
Good, where the 16,486 is the
Radicand.
radicand and the 4 is the index. Number 5, Joshua, how would we read that?
The square root of 5.
Good, because if we don't see an index class, it's an understood 2. So it's the square root of 5, where the 2, that understood index is 2, and of course the 5 is our radicand. Number 4, Alana, what do we call this, 64?
The radicand.
Good, and then the index, of course, would be the 3. How would we read that expression?
The third root, or the cubed root of 64.
And just as it's not wrong to say 5 to the third, 5 cubed is better, but 5 to the third is okay. It's not wrong to say the third root of 64, but definitely prefer the cube root. Good. Numbers 5 through 12, you were identifying the value that would make each statement true. Number 5, the square root of what equals 9, Josh?
81.
81, because 9 squared is 81. So think opposite to find the number. Lana, the square root of 256 would be?
16.
Because 16 squared is 256. Number 7, Joshua, the square root of 255.
It's 220.
Or 225, excuse me.
But 15.
15, because 15 squared is 225. Lana, the square root of what equals 1?
1.
Because 1 squared equals 1. Number 9, here we have a letter. And I told you yesterday that to take the root of a power, we have to divide the exponent by the index. Similarly, we'd seen this before. If we had something like a cubed, and I wanted to raise it to a power, like let's just say the 6th power, we said to raise a power to a power class, multiply the exponents. So to take the root of a power, we will divide the exponent by the index. So in this problem, Joshua, it says the square root of n to the 4th is, because we're dividing the exponent 4 by that little index understood 2 to get an answer of n squared. Number 10, Lana, the square root of 9?
3.
3, because 3 squared is 9. Number 11, the cube root of what is b cubed, Lana?
To the 27.
No, because let's write it out here. The cube root of b to the 27th. Remember, we just divide 27 by 3. That would equal b to the 9th. So we need something that when we divide by 3 gives us a 3. 9. There we go. B to the 9th is what we were looking for.
3 times 3 times 3.
Right. Now, if we have the cube root of 27, that's 3, because this is actually looking for an actual root. Here with letters, with exponents, you just divide them. With a root, for instance, you can't take the cube root of 9, but when it's an exponent of 9th power, that's where you just divide exponent by index. Changed your mind on it. B to the 9th is our answer. And number 12, Joshua, the square root of 324? 18, because 18 squared is 324. Numbers 13 through 18, you were supposed to prime factor each of these numbers, writing our answer in exponential form. And number 13 was a doozy, Lana.
3 to the 6th.
3 to the 6th power. Number 14, Joshua.
2 squared times 3 squared times 5.
Good. 2 squared times 3 squared times 5 is 180. Number 15, Lana.
2 times 3 times 5 times 7.
No exponents there. All the factors were primed to each other. 2, 3, 5, 7. In fact, the first 3 prime factors. Number 16, Joshua.
3 cubed times 11.
Great job. 3 cubed times 11. Number 17 should have been pretty easy, Lana.
2 squared times 5 squared times 7.
Good. Make that initial split of 7 and 100, and then you split the 100 down 10 times 10. Each of those is a 2 times 5. So 2 squared times 5 squared times 7. And then that 968 is a pretty awful looking one, but Joshua got it, I'm sure.
2 cubed times 11 squared.
Great job. 2 cubed times 11 squared is correct. Great job on that one. Questions on the homework? Questions on the homework? Yes, ma'am.
Well, just for number 16, I had 3 times 9 times 11. I
Oh,
forgot to break the
oh
9
because the
down.
9 becomes 3 times 3. That makes sense.
I only put I put 2 cubed times 11.
Okay, so forgot an 11 somewhere in there. All right, let's go and jump up above this section to the review section, 74 to 85. And let's see if we can, we may have to glance across the page, but we may be able to remember some of these. Like, for instance, the square root of 121 class, we should already know is 11. The cube root of 343, we probably don't, but glancing across the page, 7. Good. How about the square root of 169?
13.
13, because that's, just barely above 144, so barely bigger than 12. The 13 might be one we could almost guess that one. Now, number 77, the square root of x squared. Remember, divide the exponent by the index to get
1.
x to the first. Right, a single x to the first. I knew what you meant. Number 78, don't overcomplicate this now. The square root of 9 squared. 9. There's 2 ways to think of it. One way is, well, 9 squared is 81, and the square root of 81 is 9. But here's another way. Remember I said that squaring and taking a root are opposites, right? So the square root of something squared, it's as though these cancel. Kind of like having 5x equals, 10. And you say, well, let's divide by 5. Times 5 and divided by 5 cancel each other. Or if I had x plus 3 equals 7, let's put a minus 3. Plus 3 minus 3 cancel. So square and square root cancel to leave me with x. So the square root of 9 squared, the square root and square cancel to give me 9. Look at the next one. The cube root of x, or the cube root of r cubed. R, because the cube and the cube root cancel because they're exact opposites of each other. Does that make sense? Or you could think 3 divided by 3 is 1, so r to the first. All right, number 80, the cube root of 8.
8 cubed? Wait, no.
The cube root of 8. That's 8 cubed. We want the cube root of 8. What times itself 3 times?
Oh, 2.
2. 2 would be our answer. How about the square root of 10 for number 81?
100. You said square root of 10.
I'm sorry. Square root of 100 is class 10. My bad. It's a Friday for me as well. Number 82. Here we go, Lana. Without looking, the cube root of 512. You just looked at it a second ago.
I know. 8?
8. There we go, because 8 cubed is 512. So the cube root of 512 would be 8. How about that next one there, Josh? I tried to look at lines and couldn't see it quick enough. The square root of m squared, Josh? M. Lana, the cube root of z cubed?
Z.
Z. And the square root of 361. Glance back across the page. 19 is our answer. Good. All right, flip back across the page, page 505. Flip back a page 505. And I want you to remember this statement that I said a moment ago. To take the root of a power, class, we will divide the exponent by the index. Now, remember, division can be shown several ways. I could write this as a to the 18 divided by 6, and hence I would get a cubed, right? But the best way to show division in algebra is with a
Fraction
fraction bar. So if I were to have 18 to the, or a to the 18 divided by 6, that would give me a cubed as well. And so a fractional exponent really is simply showing you that there was a power and there was a root of the power, the 6th root of a to the 18th power. So if you look at the examples there, they show a 2 to the 4th, and they have a square root of 2 to the 4th. Do you see that? Look in the second blue box on the top of page 505. In red, they have a square root of 2 to the 4th. Well, one way to think of that is, well, 2 to the 4th is 16, right? And the square root of 16 is 4. Another way to think of it would be this. A square root of 2 to the 4th. Well, remember, we're going to take the exponent 4 and divide it by the index, which was the understood 2. But we know that 4 divided by 2 equals 2. So it's really 2 squared, which of course is 4. There's two different ways of looking at the problem. Now, where this can be helpful is with letters especially. For instance, we look at the cube root of x squared down below that little blurb about fractional exponents. Notice how the exponent 2 becomes the numerator, and the denominator 3 was the old index. We divided, fraction bar, exponent by index. Same would be true if we had the 4th root of y to the 8th. That would be y to the 8/4, or the 8 divided by 4. Of course, we know 8 divided by 4 is just 2. So in the case of that second little example there, I'm not even going to bother, quite honestly, with this. I'm not going to waste my time writing y to the 8/4. I'm just going to divide 8 by 4 and get 2. But had this been a 7/4, well, 7/4. Does that make sense? If it's 8/4, I'm doing mentally 2. 7/4, I'll go ahead and write it out. The square root of 4, you could look at it as 4 to the 1/2 power.
2.
Which is 2. The rational roots, of course, again, you just simplify and reduce down. So look in the yellow shaded box now. They have a 4th root of 2 to the 12th. I don't want to figure out 2 to the 12th. I'm going to divide the 12 divided by the 4 to get 3. So it's really 2 cubed. And that's 2 times 2 times 2, or 8, as you see there. Look at the next one, the 5th root of x to the 10th. Well, that's x to the 10 divided by 5, or in other words, x squared. Turn the page. So we're just going to divide the exponent by the index, or in some cases, if you see a square root and a square, cancel them. Cube root and a cube, cancel them. 4th root and a 4, cancel them, right? Because those divided by themselves are 1. So look at number 54. What would the cube root of w to the 18th become?
W to the 6th.
W to the 6th. We could write it as w to the 18/3, but no. I'm just going to write w to the 6th. Again, we're kind of breaking some of the rules they're putting out here.
What are A and B?
Well, again, they're wanting you to write it with a fractional exponent first. I'm too lazy, remember? If it's going to divide evenly, I'm not going to write the fraction. I'm just going to write w to the 6th, right? But I could write 18/3. Why? Okay. Number 56.
Y squared.
Y squared. Very good. Number 58.
6 squared.
6 squared. That becomes
36.
36. Good. Number 60.
R squared.
R squared. Good. Number 62.
3 to the 5th.
3 to the 5th. Now take a moment and figure out what is 3 to the 5th.
Oh, yeah.
$243.
243. Hayden wins. All right. Every day in this class becomes like the game show, Are You Smarter Than a 7th Grader? As the 7th graders back there would much rather do our math class than their geography map projects. All right, let's see, that was number 60. Number 64. Don't make this too hard. 3. Cancel the cube root and the cube, right? Number 66. 2. Cancel the 5th root and the 5. Or the 5th power and the 5th root. Cancel them away.
Oh, fuck. Wait.
The 5th power and the 5th root just cancel each other on 66 to leave you with the 2.
Yeah.
Yeah, sorry, it came out funny. I stumbled over myself trying to explain it. There's a reason every day I pray, Lord, would you give me clarity of speech? Clarity of thought's important, and clarity of speech is important. All right, go back and do the odds now, real quick. Go back and do the odds. Hey, we're not going to bother with the fractional stuff unless it doesn't divide evenly. Then we'll go with the fraction.
For number 55, do you actually, like, do the thing like 7 cubed?
Well, you can, or you can just look a little further up the page.
Oh.
Since we already did it once, it wouldn't hurt you to do it again, but we already have it on that page, so we're going to cheat the system a little. Again, next year you're not going to do those either because you're going to memorize them next year, so you won't have to worry about calculating 7 times 7 times 7. You'll just have 7 cubed memorized next year. Big time saver. That's why I do it.
Memorize it all.
Oh, you can. You have to.
Wait, you have to?
Yes.
Is it 343?
It is 343, but they already got that.
Yeah.
But I appreciate you, Glenn. Thank you, sir. All right, let's see how we did here. Number 53, class.
12.
1255.
343.
Good. Initially 7 cubed becomes 343. Number 57.
Z to the 9th.
Z to the 9th. 59.
W.
W's.
Oh yeah, W cubed.
W cubed. It's not a sixth root, so it's not that the 6 and the 6 cancel.
Yeah.
It's an understood 2. So when we get our 6 divided by 2, of course that comes out W cubed. Of course we generally would skip that in between step because we're lazy. Number 61.
X to the 4th.
X to the 4th, made the same mistake again. All right, so again, remember, understood 2. It's not whatever you want it to be. I'd love it to be an 8, because then it would cancel. Well, it's actually just a 2. Number 63.
8.
2 cubed initially, which gives us 8. Great job. 65.
K squared.
K squared, and number 67.
10.
That time they cancel each other cleanly. There we go. I want you to consider this for just a moment. If I had, let's just say, W to the 6th, and I were taking the 5th root, does that divide evenly?
No.
So how would I leave this answer?
6 to the
W
5th.
6 over 5.
W to the 6/5, the 6 divided by 5, right? So if that's the case, then if I had a fractional exponent, I should be able to turn it into a radical. Does that make sense? If a radical, I can divide exponent by index to get the fractional exponent, then if I had, for instance, a to the 2/3, I should be able to turn that into a radical. Remember, we divide the exponent by the index. That makes this the exponent and this the index. So what kind of root will we have? Cube root. And it would be the cube root of a squared. Does that make sense? So what if I had an r to the 1/2? What does that mean?
1 is the exponent, and then 2 is the index.
So what would that
square root of r?
The
square root of r to the first, or I like how Lana just said the square root of r. So in other words, a 1/2 power always means a square root. So if I said, what's 25 to the 1/2 power? Well, that would be 5, because half power means square root. That's something we'll go into more in later years. What if I had like b to the 2/5 power? B to the 2/5 power, what would that be as a radical?
The fifth power of
Fifth
b squared.
Root.
Or the fifth root of b squared.
Oh,
wrong
of b
one.
squared. There we go. All right. Let's give you another one. How about s to the 3/9?
The 9th root of s cubed.
Good, the 9th root of s cubed. Though, think about this for just a minute. 3/9 could reduce. I could reduce that to s to the 1/3, which means this could be rewritten.
The third root of s.
Good, the third root or cube root of s to the first, or just s. Notice, these are equal then. Now this again is a little bit higher level stuff. I'm just kind of throwing it out there because I had a few extra minutes, but look over there at the last thing on the bulletin board. Do you see we had a 6th root of 121? And I rewrote the 121 as 11 squared. So it's a 6th root of 11 squared. That could be, class, 11 to the 2/6, right? But 2/6 is the same thing as 1/3. Hence the cube root of 11 to the first, or cube root of 11.
Oh.
So that's what that bottom line is showing, is a way of making radicals smaller. Instead of a 6th root, which is, oh my goodness, that just sounds scary, cube roots don't sound as scary. So one of the ways we reduce radicals in Algebra 1 next year is by making that index smaller, and you can do it with the fractional exponent idea. But remember, we're lazy. So the book will show using fractional exponents, but Lazy Man says, you notice these both got a 3 in them? Knock a 3 out of them, get a 3 and a 1. Because you're doing the same thing as knocking a 3 out of these in the fraction, why bother with the fraction? But it does work that way. So anyway, just some neat stuff that we'll get into next year. You don't have to know all that. Your homework for this evening, for the weekend, is to do page 507, numbers 19 to 39. Page 507, numbers 19 to 39. And you can tell I'm excited about next year, Algebra 1, getting to teach you all this cool stuff. But we gotta wait, We gotta stick with easy stuff right now. It's 8th grade math, okay? But next year we'll do fun stuff. Anyway, have a wonderful rest of your day and have a wonderful weekend. And you'll be dismissed when the bell rings.